Silicon has been around long enough. It's time for a younger and far more fit challenger to take over semiconductor material dominance. Gallium nitride power devices are smaller, faster, more reliable, and comparably priced. At this point, there are a few reasons not to use GaN FETs and ICs. The GaN Talk Podcast is a series of interviews with the people behind the rise of gallium nitride in power electronics. This interview-style podcast series talks to the visionaries, leaders, researchers, and engineers using gallium nitride to disrupt the power electronics industry.
Welcome and thank you for joining us on the GaN Talk Podcast. Our guest today is Alex Lidow, CEO and co-founder of Efficient Power Conversion. Welcome to the first episode of the GaN Talk Podcast, Alex.
Hey, thanks very much, Rick.
You know, before we get into the questions, I wanted to just for our listeners and for our viewers, talk about GaN. I can remember several years ago when we were at APEC, and GaN was, at the time, wasn't as ubiquitous as it was when we just came back from APEC in Houston or PCIM in Europe. Back 7 years ago, still was quote unquote a evangelical type of product line. There was some talk about it, but silicon was the dominant factor at the show. So here we are 7 years later, we're at APEC in Houston, and GaN, or wide bandgap, is everywhere. We saw that in Houston at APEC, we see that at PCIM in Europe. But here we are today, we still have these roadblocks, these myths, this perception is reality thing about pricing, ease of use, and reliability. So we want to thank you for joining us today. And we're going to ask some questions to dispel these myths for the power electronics engineers. So let's get right into it. Let's get into the first question. Do GaN FETs and ICs cost more than silicon-based power MOSFETs and ICs?
Well, the answer is basically no. In 2015 was the first time we crossed over the cost barrier with MOSFETs. And since then, GaN has been continuously pacing MOSFETs price declines, maybe even outpacing them. So today, if you look at the EPC cross-reference, put in your MOSFET part number, and you'll see most of the time GaN will be priced in the middle of the pack. It's not the cheapest, it's not the most expensive either. And in high volumes, we are extraordinarily competitive. Companies that are aggressive in their markets and want to gain market share have found that out. And that's how we've gained many high volume customers where they actually displace power MOSFETs directly.
Right. So another question or myth that we see and that we hear from engineers is that GaN FETs and ICs are harder to use. The ease of use, they're obviously very fast devices, and it does take a power engineer to up their skills. How do we respond to that?
I think it's partially true. It is a little bit harder because it's maybe similar to driving a Ferrari at high speed compared to driving a stick shift Volkswagen. It takes more refined skills. Now, the GaN devices are much faster, so they're sensitive to layout, particularly parasitic inductances. Also, there are fewer peripheral components available, drivers and even controllers that are fast enough to keep up with GaN. Now, that part's changing rapidly. Plus, EPC is launching many integrated circuits that take away a lot of the problems of finding peripheral components like drivers or level shifters. And this integration is focused on taking away the sensitivity to layout as well. So I think that, if people want to be at the leading edge in their industries, the difficulty of using GaN is much less than it was a few years ago. And in some cases with our integration, it's even easier than silicon.
Right. So GaN devices from EPC are very small. And one of the things that we've heard from customers over the years is I'm having some issues thermally with these devices. Thermally, it's a problem, it's a challenge. How do we respond to those that are using the devices now, or maybe those that are on the fence thinking about using them, but have this myth or this roadblock in their mind that, boy, if I use this device, I'm going to have some problem thermally?
Yeah, we hear that quite a bit. GaN devices for the same power handling are about 5 to 10 times smaller than a MOSFET. However, the chip scale packages that we make and even the packaged devices, which are virtually chip scale, they just wrap a small piece of epoxy around our device, are about 6 to 10 times more efficient than the MOSFET packages for the same size. So you actually gain it all back and more because the GaN devices don't dissipate as much heat. They are more efficient in the circuit. Because of the high speed, there are less switching losses, so they tend not to run as hot. And then they are much, much easier to cool down. So you really can't harvest all that extra power density. A cooler device in a much smaller size.
Right. Now, this next question, I read a great quote this morning and I wanted to share it. Testing leads to failure and failure leads to understanding. That was Burt Rutan. He's an aerospace engineer, was responsible for Voyager back in 1986. And I know that efficient power conversion has been leading the way when it comes to gallium nitride reliability testing. GaN is not reliable. That's another myth that's out there. What do we say to the power engineer who has that thought or that idea?
Well, it's just not true. And usually the people who are purveying that myth are silicon MOSFET providers. And the reason is that GaN is proving to be much, much more reliable than power MOSFETs. And it starts off with the fact that GaN is a wide band gap crystal, which has, because it's wide band gap, that is a result of a tighter chemical bond between the gallium and the nitrogen compared to the silicon atoms in the silicon crystal. That tighter bond means it's harder to break the bond. And so it means that GaN is much less sensitive to temperature effects than silicon, for example, and operates quite happily at very high temperatures. And therefore, at the normal temperatures that we run circuits at, GaN is basically not even thinking about the temperature at that point. And the other thing is that EPC has spent an awful lot of time taking our devices and back to the Burt Rutan quote that you made a few minutes ago, and destroying them. Right. Basically flying them until the wings fall off, and then analyzing why the wings fell off, and then making stronger wings. And we've been doing that for years. So over those years, we've developed a very good understanding of the root cause failure mechanisms. And we bolstered the devices in all those places to make these things the most rugged devices I think ever made. We have over 400 billion hours we've documented in just automotive and telecom applications with only 3 failures, and those were 5 years ago for a problem that we fixed at the time. That's 2 orders of magnitude better than the best MOSFET data reported, and we're not alone. Other GaN companies are also reporting similar results, as are our customers.
That's amazing. Now, I know for our listeners on the podcast, if you're listening, we also have this on our YouTube channel, the video of this episode. And Alex, you talked about that, and I know that you are a big proponent of textbooks. And this goes back to your days as the head of International Rectifier at CEO. So GaN devices, GaN power devices and applications has a whole section on reliability, as well as other things about DC to DC, motor control. Go to the EPC YouTube channel, subscribe and like. You can go to the EPC website and get a copy of this book. But I know that this is a very popular book, and it'd be a potent tool for the engineer in their toolbox.
That's right, Rick. And by the way, the chapter 2 also has extensive tables on thermal properties of our devices, and also using them in a thermally managed system.
Great. Well, Alex, I want to thank you for taking the time today for our first episode of the GaN Talk Podcast. And for our listeners and our viewers, thank you very much.
Thanks, Rick.